Welcome back. So last time we talked about charging by conduction, which requires contact and leaves both objects with charge of the same sign, with the amount dependent on the total surface area. Now we're going to talk about charging by induction, which is by influence. So I'm going to start out with a diagram that looks very much the same. We're going to start out with a sphere that is uncharged and a rod that is not touching but close by. We have charges on the rod. It doesn't matter whether they're positive or negative. When that rod is in proximity with the sphere, the only thing that can move are the negative charges, and the negative charges are pushed away from the rod in this case, and so they accumulate on the back side of the sphere, leaving a deficiency of electrons on the other side, which shows up as a net positive charge. So the sphere is being influenced by the rod. Now, if I don't do anything else and I just take the rod away, the sphere goes back to being neutral. But I don't want that to happen. I want to create a charge on the sphere. So what I do is, keeping the rod in place with its influence on the sphere, I want to create an escape route for the excess electrons to move down and away into the ground. And so this symbol here is a ground wire, and that's a place for excess charges to move toward the ground and be distributed across the surface of the earth, much like the ground plug on your outlet. So once I allow those negative charges to escape, and then I break that wire that goes to ground, what I end up with is I still have a negatively charged rod, because it's just sitting out there influencing the sphere, but the excess negatives on the sphere have left, and so I'm left with positive charges on the sphere, which spread out as the rod is removed. And so the net result is you have a sphere with opposite sign from the rod. Okay. So in induction you get opposite charges. In conduction you get the same charges. Okay. The next thing we're going to talk about is electric forces. How hard is the push felt by charged objects when they're affected by other charges? This is called the Coulomb force. So if I have a positive charge on one object and a negative charge on another object, they're both affected by each other, and the positive is attracted to the negative, and the negative is attracted to the positive. And both of those forces are the same size. I only need one equation to calculate it, because it's kind of like the golden rule. What one does to one, the other does to the other. The way that I calculate that is force is equal to K. This is our K value. This is not something you'll have to memorize, something that'll be given. And there should be a square on that constant multiplied by Q is our charge variable. We use Q whenever we're looking at charges. I don't know why. I'm not my fault. The charge on number 1 and the charge on number 2. So it matters how big those charges are. But it also matters how far apart they are. And the distance in this equation is the full distance from one to the other. Okay, it's not a radius like a circle, it's the distance between. Okay. The direction of the force is determined by the circumstances. So the positive charge is being pulled to the right, the negative charge is being pulled to the left. They're both the same amount of force, but they're in opposite directions. If they were both the same sign, like a plus and a plus, they would be repelled from one another. And I would calculate it the same way, but I determine my direction from the circumstances. Okay. And if we have 3 different charges in a row, say I've got a plus 1 and a minus 1 and a plus 2, there will be each charge will feel affected by its 2 neighbors, even though there's something in between. So the plus 1 and the minus 1 are attracted to one another. F1 minus 1. Okay. The negative 1 and the positive 2 are also attracted to each other. F minus 1 and 2. But there's also an interaction between the plus 1 and the plus 2, and those two, being both positive, are pushing away. And so each object is affected by 2 forces. So this object has 2 forces acting on it, the one next to it has 2 forces acting on it, and the final one has 2 forces acting on it. So there are 3 objects, each of which has 2 partners that affect it, and they can be affecting it in either direction. In this case, both of them randomly have a left and a right, but that's not always the case. All right, so let's do a problem with some math in it. I've put 3 different charges on here, given you the separations, 2 millimeters between the first 2, 4 millimeters between the second 2, and we're going to do some of the calculations. So if I want to look at the effect of charge A on charge C, those are the 2 I'm going to do. When I want to calculate that, right, I'm going to use 8.99 times 10 to the 9th Newton meters squared over Coulomb squared. That tells me what units I need to use on my charges and my distances. Okay, so A has plus 1 times 10 to the minus 6 coulombs. 10 to the minus 6 means micro. And C has negative 2 times 10 to the minus 6 micro coulombs. Now those signs are going to disappear because I'm doing absolute values. And then I'm dividing by the total distance from one end to the other, which is 2 millimeters plus 4 millimeters. And that's 6 times 10 to the minus 3, because that means millimeters squared on the bottom. When I do that math, if I've done it correctly, it comes out to be 499 newtons. Okay, so that's one interaction. That is the interaction of A with C, and that's a plus and a minus. That's an attraction. So there's a force in this direction between A and C that is attractive between those two. And that's what we've calculated. Pause the video, do the other calculations. Calculate the force of A on B and the force of B on C. Let's see what you get. All right, so when we come back and we get the force of A on B, I got 6,742 newtons, and B on C, I got 3,371 newtons. Okay, those are a lot bigger, but A and B are closer together, and B is a bigger charge. B and C are closer together, and both of those are bigger charges, so that makes them bigger. All right, so A and B are an attraction, so there's a force of attraction between A and B. That is apparently fabulous. And then we have a force of repulsion between B and C. Because they're both negative. And so then we can figure out what the signs are when we add and subtract these things. So for A here, those get added together and they're both positive. And the total force on A, with both of those numbers being positive, rounded off to 2 sig figs, is 7,200 newtons. The force on B, where both of them are negative, adds up to be negative 10,000 newtons. And the force on C, with one positive and one negative, ends up with a net positive 2,900 newtons. Okay, so if we look at those, that gives us the whole picture of how these charges are being pushed and pulled. A has a net push to the right, B has a net push to the left, and C is also pushed away from the other two. If those were atoms or molecules, that would be how they were attracted or repelled from one another, and would tell us which direction things are going to move because of their electrical interactions. So this is a very important kind of calculation that gets used a lot in theoretical chemistry. All right, so I'm going to finish that up for this video. The next time we come back, we'll talk about electric fields in preparation for our lab. See you soon.